That's like a half, so that becomes like a 2. So it's like 2 times 1 minus a half to the n. So that's just like 3 minus 1 over 2 to the n minus 1. Did I do that right?
Yeah.
Yeah. Which is less than 3. Bam.
Nice.
A sub n is equal to something which is less than something which is less than or equal to something which is equal to something which is less than 3. So A sub n is less than 3. All right. As this sequence is bounded above, in particular we showed that its upper bound is 3, and increasing it must have a limit, and somewhere in the 3-ish range, a little bit less. We call that number e. Cool?
Cool.
All right, that was pretty fun.
Can we talk about the LUB axiom?
Yeah, sure, we got 6 minutes.
Plenty of time.
Oh shit.
We didn't have French.
Finish the thing. No, we
Luke took a nap for 20 minutes, woke up and realized that he should have been doing his French homework.
Which was not existent today.
It was existent. Finishing the script. Finish all 30 lines.
Oh no, we're just gonna wing it. Vika and I are gonna wing it.
So, good. So, what is the least upper bound axiom? Are you back over here? Oh, camera's back over here. Okay. So, basically, yeah, it's this property that the real numbers have. And it's kind of like, okay, so maybe first little vocab, right? You can say, so what is, oh, bad marker. So, you can always take, I think you guys already know this already. Did we do stuff like this? Yeah, we did. The max, yeah, we don't need to. Everyone knows what an upper bound is?
Yeah.
An upper bound of a set is just a number which is bigger than every number in that set.
Yes.
Okay. So, a so-called least upper bound.
Bigger than or equal to, right?
Yeah. Yeah. A least upper bound for a set A. Least upper bound is, well, 1, it's an upper bound. It's an upper bound. And also, it's less than or equal to any other upper bound. Any other upper bound. Okay. So, yeah. So basically, a least upper bound is the smallest number which is greater than or equal to every other number in a certain set.
Yeah.
Okay, so this is something that's called a supremum, which is like, just a Latin word for the same thing. So suppose you have some finite set like this. What is the least upper bound of the set 6, 8, negative 3? 8. 8 is the smallest number which is greater than or equal to every one of the numbers of this set. There are other upper bounds, like 9, but 8 is the least upper bound. Okay, what is the least upper bound of the set of real numbers from negative 3 to 4? 4. 4 is the least number which is greater than or equal to all those numbers. What is the least upper bound of the set from negative 3 to 4 open?
4. 4.
It's 4.
It's still 4. 4 is still the smallest number which is greater than or equal to all of those numbers. But notice that in this case, that number 4 was not in the set itself. Okay, so sometimes it's in the set, sometimes it's not. What is the least upper bound of the set of all numbers of the form negative 1 over n, where n is a positive integer?
0.
Yeah. Okay. Here comes an exciting one. What is the least upper bound of the set of all rational numbers which are positive and when squared are less than 2?
Root 2.
What is the smallest number which is bigger than every number in that set, which is the set of all numbers which when squared are less than 2, is root 2. Now root 2 is not rational, that's true, but it's still like a number, right?
Yeah.
Okay, and that really gets to the essence of the issue. Sometimes the least upper bound is an element of the underlying set, and sometimes not. So, a set, this is getting very abstract now, so a set S has the least upper bound property if and only if every subset A of S, every subset A of S, which is bounded above, put that in parentheses, has a least upper bound in A. Okay, what the hell is this saying? In other words, a set has a least upper bound property if anytime you take some of those numbers and you construct the least upper bound of those numbers, then the least upper bound is one of those numbers. So, for example, do the rational numbers have the least upper bound property?
No, this should not.
Yeah, no, because we have just demonstrated a set which is a subset of rational numbers for which the least upper bound of that set is not a rational number. Follow?
Shouldn't it be L, U, B, and S?
Yeah.
In S. Okay, sorry. What about the real numbers?
Yeah.
Yeah, they do. The real numbers have the least upper bound property, and that is the thing distinguishing the real numbers from the rational numbers.
Is there any way to prove that?
Eventually
Just
determined.
an
No,
axiom?
it's like just like an axiom. Interestingly, the integers.
I don't know. It kind of seems like they do.
If you take a subset of integers, which is bounded above, what's the least upper bound of that set? It's just the biggest one. So this actually does have, the integers do have the least upper bound property. So basically, and I can even write, no, there's no point in doing that. So basically, so what are the real numbers? This is a good way to end the class. It's kind of like how we started them. The real numbers are, they are they're a set of objects obeying all the field axioms, and they have the least upper bound property. Sometimes called the least upper bound axiom. Some people also call it the completeness axiom. The idea is that the real numbers, they're all there, man. You have a line, and you have like a number root 2, and you look at all the numbers that are getting really close to root 2, and you look for root 2, it's there.
How do you prove there doesn't exist some other set that satisfies the super?
What you do is you show that any other set which does satisfy all this is essentially like isomorphic to the real numbers. It might as well be the same thing, you're just calling them something different. This is way too much advanced math going on in this class. Okay, bye Armel people, turning off the camera.